Hi, everyone. My name is Laura Line, and I'm pleased to welcome you to the National Academies of Sciences, Engineering, and Medicine, and to our monthly webinar series, Climate Conversations, Pathways to Action. Our conversation today will be recorded and available to view right here after the event. If you'd like to ask a question, please submit them in the Slido box below the video at any time, and we'll incorporate them into the Q&A section of our programming. We also encourage you to participate in the polls that will appear in the same location and give your feedback after the event in the survey linked above the video. As a reminder, the views expressed in each conversation are those of the participants and do not necessarily represent the National Academies. For today's climate conversation, Powering AI, I'm so thrilled to introduce my colleague, Kasia Kornecki. Kasia is a Senior Program Officer with the Board on Energy and Environmental Systems and co-director of the National Academy's recently launched Roundtable on Artificial Intelligence and Climate Change. Over to you, Kasia.
Thank you so much, Laura. So before we dive into today's conversation, I'd like to take a moment to share some background on the work that we've been doing at the intersection of AI, climate, and the broader energy transition. I have the honor of co-directing our roundtable on AI and climate change, and that group is focused on two main goals. One is improving the beneficial uses of AI, such as in energy system optimization and weather forecasting, and two, mitigating AI's potential impacts on climate. So as part of that mitigation effort, last November, the Roundtable hosted a workshop on data center energy use and emissions. And I'm very excited to say that we will be releasing a summary report of that workshop later this week. And one of our speakers today, Cooper Ellsworth, participated in that workshop, and he will be joined today by Yuri Dvorkin, who is a member of our roundtable. So I'm excited for this lineup. And if you're interested in hearing more on this topic, the roundtable will be streaming a panel discussion next Monday, where we'll reflect on the workshop's findings and explore future directions for analysis and collaboration at the AI Climate Nexus. Beyond the Roundtable's work, the National Academies have also been active in related areas. We've been publishing reports on accelerating decarbonization, using AI for scientific discovery, and addressing issues like electricity system reliability and the deployment of new energy technologies. I encourage you to explore the links on this event page if you'd like to learn more. So now, without further ado, I am very pleased to introduce the moderator for today's conversation on powering AI. Kristen Hayes is the Senior Director for Research and Policy Engagement and co-host of the Resources Radio podcast at Resources for the Future. She originally joined RFF in 2009 to support a large-scale, multi-layer project assessing the effectiveness and costs of a range of national U.S. energy policy options. Kristen, the floor is yours.
Thank you so much, Kasia. Well, it's great to see so many people on this webinar today. I do think that's an indicator of the very deep interest in this topic. And as Kasia mentioned, there is a lot of conversation happening around AI and greenhouse gas emissions, but I think the appetite for more is great. And so I'm very pleased to be having this conversation today with Cooper and Yuri. So just to give a little bit more context, and then I promise I'll turn quickly to our two conversationalists, but yeah, so the data centers that underpin AI usage currently require quite a bit of power, electric power that is, contributing to growing demand for electricity in the US for the first time in decades. After decades of sort of stable demand, now it's headed back up. And how to meet this new demand while maintaining reliability and affordability is on a lot of people's minds. And moreover, many of the companies that are heavily investing in AI also have long-term emissions reduction commitments. So there's a strong interest in understanding where and how that increased demand can be met by clean energy. Also, for another important piece of context, even before this growth in demand, the US grid was facing challenges related to aging infrastructure, long queues for interconnection, particularly for renewable resources, the need for new pricing structures and market designs, and much more. So how AI presents both new challenges, but also new opportunities for the power sector is really at the heart of our conversation today. So with that, I'm very pleased to welcome the two primary conversationalists for today's webinar. So first, Cooper Ellsworth leads Google's AI and Cloud Emissions Program, where he measures emissions across Google data centers and their workloads. With a background in climate tech software and climate science research, he develops actionable data for corporate carbon accounting and decarbonization efforts. And of course, the second conversationalist is Yuri Dworkin. Yuri is an associate professor at Johns Hopkins University. His research focuses on energy systems modeling to support the transition to a low carbon society. And he emphasizes energy policy, planning, operations, and market decision making in his research. So Cooper and Yuri come from different sectors. They offer different perspectives, but both bring deep expertise and thinking about these issues. And I think all of our viewers are in for an awesome conversation today. So, okay, let me start by asking you both, Yuri, I'll start with you, and maybe you can just say a little bit about what brought you to this space, this intersection of AI and emissions reductions, and then I'll turn it to Cooper to answer the same question. So, Yuri?
Sure. Good morning, everyone, and thank you, Christine. Thank you, Laura. Thank you so much, Keisha, for this invitation, and to the National Academy for paying attention to this very important topic. I'm looking to having this conversation with you all. What attracted me to this topic is an understanding that AI has penetrated so many spheres of our lives, and we have very little understanding what connections we have and what impacts it creates. And if we compare the impact of AI on our lives with, for example, of transportation, we have very easily built connection between like fueling our cars, how much it's going to cost, how long the car would go, what are the mechanisms for climate impacts, and so on and so forth. We don't have this kind of understanding for AI. And as it becomes even more important part of our lives, I would like to better understand how we can do better by the planet and by our society.
So the new frontier in a certain sense. Yeah.
Yep.
Cooper, what about you?
Yeah, thanks for having me, Kristen. I'm excited for the conversation as well. My background is mostly in data and analytics, and I think it's an interesting space to kind of bring real granular data to bear on this question of how AI energy and emissions is growing. So where companies have been measuring and disclosing emissions for decades now, sometimes those disclosures are less granular than you need to really target emissions reductions opportunities. And so my background really brings more actionable data to bear on these questions. And being at Google actually is a particularly interesting place to do this because so much of Google's carbon footprint does come from electricity. Mm-hmm. And electricity actually of our data centers is actually pretty well measured by the machines and the power of those machines consume. And so while other companies might have fleets of vehicles where they need to add telemetry onto those vehicles to understand kind of the where they're going and what the mileage of those vehicles ends up looking like. We actually have this data directly available to us. And so I get to play around with that data on a day-to-day basis. And obviously with this AI load growth question starting to become more and more high scrutiny, we've applied a lot of the data sets that we've developed to monitor the emissions of individual workloads to this question of how to understand the emissions of AI and how we can get more transparent on that as well.
That's great. Yeah, I feel like I have two very data-driven folks on this conversation with me, so I'm sure we're going to get a lot of, actionable data, as you said, Cooper, just thinking about how to really turn data into practice. That's great. So let me ask you both one more landscape question, and I'll ask you in just a second, but before that, I just want to remind folks of some definitional terms here, the taxonomy of greenhouse gas emission types, because I know that's going to come up very shortly and probably has relevance for our whole conversation. So just quickly to remind people that greenhouse gas emissions are generally categorized into 3 scopes. And I'm going to rely on the EPA's definition of those. So scope 1 emissions are direct greenhouse gas emissions that occur from sources that are controlled or owned by an organization. That is emissions associated with fuel combustion in furnaces, boilers, etc. Scope 2 emissions are indirect greenhouse gas emissions associated with the purchase of electricity, steam, heat, or cooling. And then scope 3 emissions are the results of activities from assets not owned or controlled by the reporting organization. They are also sometimes referred to as value chain emissions. And I think, as Cooper has already indicated, they often represent the vast majority of an organization's total greenhouse gas emissions. So with that definitional framework out of the way, let me turn to both of you for this kind of landscape question here and ask, what are the main sources of emissions associated with AI? So Cooper, let me start with you.
Yeah, so I can jump in fairly deep maybe as we start, because we just actually released a paper in January of this year measuring the total life cycle emissions of an AI hardware chip. So as folks may know, there are GPUs, or in Google's case, TPUs, that are used to train and ultimately serve AI models to the users of those AI models. You can imagine tracking one of these chips across the entire life cycle of its development, manufacturing, usage, and ultimate disposal or retirement of the chip. And the paper that we pulled together was basically trying to measure the emissions along the entire life cycle. It's called kind of a life cycle assessment approach, and understand the relative sources and hotspots of emissions along that life cycle. So if you break down the life cycle of one of these chips, you can imagine it broken down into the manufacturing of that chip, which includes raw material extraction, refinement of those materials, and manufacturing, the transportation of the chip from the source of its manufacturing to the data center itself. You have the ultimate usage of that chip and the electricity that's used to run that chip, be that clean or maybe more dirty energy sources. And then once that chip has gotten to its usable life cycle, then either you recycle or dispose of that chip. And what we found basically, along Kristen's taxonomy of scope 1, 2, and 3 emissions, was basically that about 10 to 20% of the entire life cycle emissions of the chip comes from scope 3. And the majority of the emissions come from scope 2. And so that's a really powerful and important insight, because that, I think, starts to ground the conversation for Yuri and Kristen and I today, and that the majority of the emissions are coming from the operational electricity usage of the chips doing the computation in the data centers. But the important aspect of that is that clean energy procurement ends up being a relatively straightforward lever for us to start to reduce the emissions of those chips, especially compared to reducing the emissions associated with manufacturing those chips, when you think about the things that need to be done in your supply chain and value chain in order to reduce the emissions there. So I guess just to kind of maybe round out that question and pass it over to Yuri, I think that's why it's so important for us to critically think about what the impact of these chips and these models are on the energy system. As Kristen mentioned, there is this increase in electricity load growth from AI, but it's also an opportunity for us to rethink how the grid responds to the load of these models, because that was going to come from any sector, regardless of necessarily which sector was going to electrify most quickly. And so I think it's an interesting question around what can we do as the tip of the spear as the data center industry to help to push the grid and to be more renewable and more clean.
Mm-hmm. Yeah, and I do think that's where the opportunity part comes in alongside the challenges for sure. So Yuri, what would you like to add about the kind of AI emissions profile?
I think you, Kristen, and you, Cooper, you teed me well. Just to say that life cycle assessment is extremely important. And one thing that we need to recognize is that all scopes 1, 2, and 3, there are different levels of interdependency between them. It is true to say that scope 2 is by far the largest source of emissions, and there is a lot of that we can do. We can use chips more efficiently by improving performance of algorithms and by using better scheduling techniques, so using chips more efficiently. We can have better building control and HVAC control to make sure that cooling works properly. We can use better and more efficient building envelopes. But all of this rests on the assumption that we have clean energy procurement or cleaner energy procurement. And that raises an entirely new host of questions. How do we enable clean energy procurement for data centers? Because it's an unprecedented amount of power that is being added over a very short period of time. And we need to make sure that while we have ways to procure this electricity in a sustainable way for data centers, because it's a requirement for many corporate users that they want to use sustainable AI and sustainable computing, we also don't make the grid dirtier by itself. Because if all clean resources all of a sudden repurposed towards AI, it means that other loads will be served by not so clean resources. And that's what brings me to the point that Cooper made earlier, that we need to make sure how emerging accounting frameworks will be adopted to reflect this fact that we account for the holistic grid impacts of AI in a consequential manner. And the key here is to better understand respective demands, to better understand flexibility of AI loads, and how this flexibility can be leveraged to better coordinate data center operations with with the power grid, and maybe somewhere we can find low-hanging fruits and to really cut Scope 2 emissions. But Scope 2 emissions, as I said before, they account for roughly 85, 87% of the life cycle that Cooper mentioned before. And what remains from like 10 to 15% in Scope 1 and Scope 3 emissions. It's remember to keep in mind while the relative share of those emissions is small, as AI infrastructure and AI use in our society expands drastically, this small relative percentage turns into fairly large emissions numbers. And we need to make sure that we exploit interdependencies between Scope 2 and Scope 1 and Scope 3 emissions to optimize them as a system. And that's why we need to push towards like life cycle assessment across all stages.
That's great. This is wonderful. You guys are setting this up so well for our subsequent questions and conversations too. So yeah, I've heard a lot about the need to think holistically and to focus on kind of life cycle analysis here. I want to take a little bit of a deeper dive into some of what we started talking about. I want to encourage our listeners as well to make sure to be putting those questions into the Slido box. That is the kind of main portal for questions. We're going to make sure to hold on to a long time for those questions. So there's my plug. Now I'll go back to my conversationalists here. So there's so much to talk about here. So Yuri, I'm going to start this next kind of deeper dive section with a question for you. It's actually like a 4-part question. I couldn't get it down to just one question. So here we go. But so you focus a lot in your research, in your field of study on energy systems modeling and on planning. So from those perspectives, when you're thinking about how to plan, what kind of energy demand should we be preparing for? We've talked about it going up, but how much up? And what should we be preparing for? And then my second/third, fourth part is, so as this demand for electricity accelerates, where do you see the biggest stress points being for the grid? We've talked about the importance of being able to add power to the grid. So where are the biggest stress points and how would you potentially tackle them? If you have solutions that you'd want to flag, would love to hear how you're thinking about that.
Absolutely, thank you. It's a very loaded question, so let me try to unpack it for us all. And Cooper, feel free to jump in if you feel that I'm getting carried away, because I can talk for a long time about this topic. So the first thing about the demand growth is that AI is not the only sector that would like to tap into our power grid, and the AI sector needs to compete with all of the other sectors that have been growing over the past several years, like electrified transportation, electrified heating and cooling of buildings, and so on and so forth. So we need to understand that electricity supply is very limited and there is a lot of competition from other sectors. The other thing that we need to keep in mind is that AI demand is extremely lumpy. We're talking about the deployment of data centers, that unlike an electric vehicle, which comes on the scale of, say, 100 kilowatts, data centers come on hundreds and gigawatt scale. So we will have to add lumpy quantities of power demand to the grid. So taking into account the tremendous use of AI in all aspects of life and its unique characteristics of being added in lumpy quantities, we have to realize one important thing which differentiates it, that it's going to be very concentrated demand and it's going to be demand on the gigawatt scale. When you take this into account and you realize that in some parts of the country, electric power demand will grow by more than 10% per year. For example, it's going to be some parts of Maryland, some parts of Virginia, where you might have seen a lot of announcements about data center deployment. As countrywide, for the first time since 1950s and 60s, we're going to have electric demand growth greater than GDP. For example, in terms of the US, recently there was a correction for the economic growth, and the lower bound is 1.3%. And for both 2025 and 2026, electricity demand from AI is going to, the overall electricity demand from all sectors is going to grow by up to 3.5%. So you can see this discrepancy that the economy is going to grow slower than electricity demand. That makes traditional tools to account for AI growth in need of some modifications. And in addition, by complications related to predicting the exact demand, there are also issues related to basically how do we account for it in the models. And there I would emphasize three challenges which we haven't seen before at that scale. First, the challenge related to time, that nothing can be built very quickly and very rapidly. And in that sense, data centers will be deployed much faster than the grid could possibly react. Just to give you a few examples, since early 2000 in this country, there were only 3 nuclear power plants built, and they took 10 plus years to be constructed. This is not the time scale that is going to be satisfactory for AI loads. They need it much faster. So if we cannot build nuclear, which is a source of low carbon power, what can we possibly build? Short term, typically we can build natural gas, but in this particular situation, we are strained because there are supply chain crises for gas turbines, and we cannot deploy them as quickly as we previously thought. And renewables remain a viable option because what they can be achieved with renewables is that they can be deployed locally, and they have fairly short lead times. What complicates this is that due to recent changes in trade policy, renewables are likely to be more expensive, especially those that are produced abroad. And that puts us in a position to kind of assess what kind of options we have which are cost competitive and can be deployed in time. And investors, what they really care about is return on investment, right? And from that viewpoint, they have a lot of uncertainty on the supply side. They have a lot of uncertainty on the demand side. And we need to find a way to coordinate these uncertainties in a way that help us to move forward. And the landscape is getting more complex and more complex with every month. For example, recent advances with DeepSeek, they introduced an additional layer of uncertainty how much these models will consume electricity in future years. Maybe demand that we need is not that great, and so on and so forth. This question needs to be addressed in a proactive manner. And the third issue which exists here is complexity, because it's not only about building power plants and understanding the effects of new models. It is really about the coordination, this very complex supply chain and value chain of AI loads and data centers in the context of power grid. It's not only about generation, it's also about transmission. How do we supply electricity from the places where it's being produced to the places where it's being consumed? And how do we make sure that we can possibly create this infrastructure on a quick time, because transmission takes a lot of time? Another opportunity is to leverage storage. Battery storage, for example, can help us to synchronize peaks of renewable energy production and peak of AI use, minimize waste of solar energy, which happens in California and ERCOT fairly clearly. And the final point that I would like to make about the challenges is that AI use is fundamentally driven by the needs of consumers, which can be both corporate and personal. And we need to better understand in terms of what flexibility exists on the consumer side so that we can make it part of our life cycle assessment, and we can incentivize behavior which help us to cut on scope 2 emissions. And if we find a way how we can reduce our scope 2 emissions, that might possibly trickle down on scope 1 and scope 2 emissions, scope 3 emissions, because we're going to have different downstream use scenarios, and we probably will have different requirements for scope 1 too.
Yeah, that's so sort of a great comprehensive setting for all this too. And what I'm hearing is, there are challenges. I love the phrase lumpy demand. I'm going to use that all the time now, but there's sort of temporal lumps. There are geographic lumps. There are levers that we can use all over the place, but they really have to be sort of looked at, again, holistically. We're coming back to that word of what a big and complex problem this is, and sort of the need to look at it holistically. Cooper, is there anything you'd want to add kind of on that question? And then I've, of course, got a question for you too, but I want to give you a chance to weigh in on that if you have any response or thoughts.
Yeah, just very maybe quickly, I think there's just a large opportunity to also think about the future of data centers generally, and kind of how you can design data centers that work well with the grid, especially kind of as it becomes a growing proportion of the total grid load. And so that's something that I think collaborations and pre-competitive groups are thinking about to kind of start to bridge the gap, not only just with corporates thinking amongst themselves, but talking with the policy folks and the folks who are at utilities. And that's a thing that that many of these hyperscaler data center companies are really have ambitious goals for, I think, is to make sure that they're not only developing data centers that can be resilient to changing electricity grids, but also the fact that they have very strongly held commitments on sustainability and climate as well.
Mm-hmm. Yeah, just one more thing I wanted to flag too. Another area where I think there is a lot of work happening is around the speed question that you mentioned. There's this disconnect between the speed at which we've traditionally built things in this country and the need to sort of move faster here. So I think that's another area where these you use the word collaborative or something like that in your answer, Cooper, and I'm thinking about similar collaboratives and bipartisan ones as well around how do we, move forward on permitting and siting and availability of infrastructure more quickly as well. So a very important conversation, something we're deeply involved in at Resources for the Future for sure. All right, Cooper, I want to give you a chance to talk about your favorite topic, the data part. So what do you see as kind of the current challenges and opportunities in AI optimization and emissions measurement, your kind of heart of your work here, and how can that emissions data for AI be standardized, be made more transparent? What are the ways to really move forward on the kind of measurement side?
Yeah, I'd love to start with the opportunities, and I think some of the things that make me really kind of excited about working in this space. I think the first one is just the tailwind that a lot of the objectives that we have on the sustainability side are actually fairly aligned with the business objectives of reducing the energy consumption and the costs associated with developing and serving these models. I think it's kind of interesting and important for people to note that not only do we want to reduce the energy consumption of these models from a sustainability perspective, but there's a lot of work going into the fact that energy efficiency reduce those costs as well. So as I alluded to in that paper that we published in January on the hardware side, we actually show about a 3 times more efficient TPU that we developed in terms of carbon efficiency. And that also goes back to energy efficiency as well. Showing that on the hardware side, there's really important gains that come from designing more and more efficient hardware that these workloads are being run on. And I think even more compelling is actually the software side, as Yuri alluded to as well, potentially with DeepSeek, but the model side actually sees more and more opportunities for gains in terms of the energy efficiency for a given output. So maybe people probably see the AI overviews that come to the top of their search requests for Google search. And actually, we've seen that over the last 18 months, there's about a 90% reduction in the cost per query per search. And you can imagine that that also kind of feeds back into the energy per query. But we shared that as a cost per query number externally. I think also maybe to kind of move from the opportunities to the challenges, I think one of the big challenges is actually just transparency in terms of this data being shared externally by many companies. And a lot of the transparency challenge comes from a lack of consensus, I think, really around how to share these numbers in a way that is consistent across different companies. So you feel like you can share numbers that will be comparable in an apples to apples way. And that's what we'd also tried to kind of put out there as well with that white paper, was to try to have a comprehensive LCA style inventory of what AI emissions look like, so that other folks can start to kind of see what that looks like and maybe start to present their own emissions in a way that they feel like won't mean that it's a race to the bottom in terms of how someone is interpreting something like the greenhouse gas protocol.
Yeah.
I think maybe just quickly another opportunity is actually ensuring also that the electricity that's powering AI is really clean. When we go back to thinking about the greenhouse gas protocol, which is the core standard for how to measure and disclose carbon emissions, it actually allows for relatively coarse accounting of clean energy being applied to energy consumption. It allows for you to match clean energy to energy consumption at the annual scale and also within a country. And Google actually is really pushing for 24/7 style accounting, where you are required to match clean energy consumption with the production on an hourly basis, and also within the grid that the energy is being generated in. So we think that's a really important next step as well, to make sure that when folks make claims around the emissions of their AI models, that it's being done in a way that's actually making sure that the grid is being built in order to power those models when the energy is being consumed. So I'd say like those are kind of maybe the two opportunities, but transparency, I think, comes from both of those, because I think we want to be more transparent. The consumers of our products also want us to be more transparent, and it'd be great to see more companies starting to jump into that as well.
Cooper, I'm going to spring a follow-up question on you, but where's the demand for that transparency coming from? You mentioned consumers. Who are all the forces that are driving the transparency that you're talking about here?
Yeah, I think you can probably break it down into both enterprise customers. So those are customers of Google's and other companies that are corporates that may be sitting in Europe, where things like CSRD are requiring them to disclose emissions, or aspects of things like the AI Act are asking for companies to disclose the energy consumption of AI models. And there's a lot of demand by different customers of data center providers to be more transparent. And we actually have a tool in our cloud carbon, or in our cloud suite, that actually gives the carbon footprint of the workloads that our customers are using, which I think helps them get more transparency into that. And we're trying to improve that to be more transparent about the AI emissions. And then when it comes to consumers themselves, so folks that are using Google Search and Gmail and Google Maps, they're also starting to kind of demand more transparency. There's different subsets of consumers that have desire for the products that they use to be sustainable. And I think that does feed back to decisions that are being made by corporates, because they obviously want to serve customers as best as they can.
Thanks. Yuri, anything you'd want to add on the measurement side? You're very welcome to. Otherwise, I've got yet another question for Cooper as we go even deeper into this topic.
I just want to comment on one thing, that the last point that Cooper made about user preferences, it was music to my ear, because in order for us to make sure that we minimize user impact, we'll have a chance to better understand their behavior, that would require a collection of more data, and user cooperation would be very important to understand what opportunities there exist, especially when prompt engineering becomes so important and has its own cost to the company that runs AI, and eventually to the emissions. Recently, it was announced that every time you add please or thank you to your ChatGPT queries, apparently it has a pretty rounded dollar cost. So having access to end users of AI, whether corporate or residential, would be existential to make sure that like holistic lifecycle assessments would actually work in practice.
Great. Okay, I definitely want to make sure I'm leaving lots of time for audience questions. So I'm going to ask you both, I'm going to take my moderator preference, ask you both one more question each, and then we'll turn to the audience. So Cooper, I'm going to start this one with you. And this really does build on the topics that you were just mentioning around efficiency in particular. So you mentioned a number of improvements in efficiency that have been happening already. And I wanted to ask you to dive just a little bit deeper into how the industry is currently incentivized to prioritize those energy efficiency and emissions reduction goals alongside the clear desire for better computational performance. Either how are they incentivized now, or how should they be incentivized moving forward to continue kind of improving in that area?
Yeah, I think I alluded to it a little bit in my previous answer, because it just ends up making sense for the business. We want to have kind of lower and lower cost models and lower cost serving. And so we want to reduce the energy consumption of those models, which in turn reduces the environmental impact. But also things like regulation, like I mentioned, like the AI Act kind of requiring or asking for companies to disclose the energy usage of models as well. But it also comes down to the user preferences that we got to as well, when we kind of need to react to that. And I think also just being responsible, kind of stewards and trying to build responsible AI. I think we recognize that we don't want to put our sustainability commitments at risk. So Google has a 2030 net zero commitment, and then also a 2030 24/7 clean energy commitment, where we'll be running 100% of our workloads on 24/7 clean energy by 2030. And so I think those are kind of the complete kind of table of things that kind of drive us to want to develop these AI models in a responsible and sustainable way.
Yeah. And are there particular sort of advancements in efficiency in either in hardware or in, usage, any of the things that you talk about that you're particularly excited about? You've got sort of, I don't know if you can give our audience here a preview of what's coming down the pike. I'm not asking for any corporate secrets, I promise, but
Yeah.
anything that, that you see the momentum continuing that you're particularly excited about?
Yeah, it's kind of funny. Sometimes some of these things are not actually even couched necessarily as sustainability advancements. Like sometimes you need to be following the deep technical dives in these archive papers that come out on just model efficiency advancements, and then think about it with a sustainability lens. So one example of that is as kind of speculative decoding. So there's this kind of technique that's
Another
very
great
deep
phrase.
on the technical side, where essentially for inference, where you're serving the model to users, you are increasing the efficiency of the model, and that has great gains for kind of the efficiency of that model. But when you kind of realize that trickles down into the fact that it's using less energy, you can kind of start to get really kind of excited about the fact that it has a double bottom line associated with it.
Yeah, that's great. Okay, Yuri, I'm going to close my part of the questions with a big one for you, something else I've been very excited to ask about. So I would say so far our conversation has been fairly or entirely US centric, but I know you've been thinking about these issues on a much more global scale as well. So I wondered, I'm going to ask you a broad question, but sort of how are the topics that we're talking about here today, how are they being discussed in other countries? And are there any lessons that you think might apply to the US that we want to take from the discussions elsewhere?
Um, That's actually a very good question. So we can see that AI is being deployed all over the world, and there are several distinct examples that could be very helpful. First of all, software innovation can come from anywhere in the world. For example, DeepSeek came out of China, but it might have been Europe, for example. And that purely software innovation changes the way how physical infrastructure works around the globe. One of the things, speaking about China, that has been very impressive is that they do coordinate growth of AI infrastructure at the national level. This way is better suited for their way of governance. But even in the United States, where typically a lot of such decisions is left open to the market participants, right now there is an effort announced early in April by the Department of Energy to have a network of 16 data centers, which are co-located with DOE national laboratories and some other facilities, to kind of provide some backbone to the nationwide infrastructure. So in some way, America is already learning from international experience in that space. Another important thing that exists in here is that if we look around the world, and primarily into developing countries such as China or India, that they build out energy grid in parallel with their data infrastructure. They don't prioritize one technology over another. They just build across the board, coal, gas, renewables. And sometimes, as an example of China, you have massive rollout of coal power plants and even a bigger rollout of, for example, offshore wind, which still is in a nascent state here in America. Speaking about this comparison between the US and China, earlier today, Financial Times posted an op-ed by Hank Paulson, a former US Treasury Secretary, who essentially said that clean energy supply is going to be critical in order for us to win the AI race for globally. And what is interesting is that as soon as we deploy infrastructure, say in the United States or in Europe or in China, it will immediately trickle down into global south or other developing countries. And that will create a very interesting innovation loop, because data centers are such that they need to be upgraded every 3 to 5 years. And what that means is that every 5 years you will have technologies that are essentially of the previous generation, but they can still deliver a lot of value in other countries. So one opportunity for us to learn globally is how to make sure that disembodied carbon, which is already in the chips is not being wasted, that we can either recycle or repurpose those chips somewhere where they can deliver a larger incremental value than in the developed world.
Yeah, so many issues to dive into here. And I'm noticing, I'm looking ahead to the questions from the audience, and there are a couple really about these international questions. There are a lot about how do we stay clean as we ramp up on demand. So I'm gonna turn to those audience questions, and I'll see if I can continue to draw out some of the themes that we've been talking to so far. There are, as anticipated, a ton of great questions in here. Please do keep them coming. I really will try to get to as many as we can, but there are a lot of them. So apologies in advance to those we don't get to. All right, so maybe I'll start with a subset of questions that are around geography and geographic kind of placement of various pieces of the puzzle here. So maybe I will actually, maybe Yuri, I'll start with you on this one, but the questions are around, you know, are companies actually factoring in how accessible clean energy is to determining the location for data centers, where to expand them? And then, you know, in particular places, there's a question, and Cooper, you might be better placed to respond to this, but are data centers more efficient centralized versus modular and decentralized? Does that actually lead to any kind of different geographic decisions? So I'd invite whoever wants to sort of comment on the siting side of these things to feel free to chime in.
I'm happy to answer
for
first the grid part and then give it over to Cooper. So from the grid viewpoint, siting data centers is a rather complicated process, which requires some interconnection studies. So from that viewpoint, siting one data centers procedurally is easier than siting a number of small data centers, especially considering that interconnection queue is quite piled up. On the other hand, from the physical impacts, having a distributed set of data centers is more beneficial because you can alleviate the stress on the power grid. We read a study with Resurity, and it was supported by Meta, which shows that transmission constraints are kind of important. And if you don't take them into account while you do emissions accounting frameworks, then you wildly misestimate impacts of data centers on marginal carbon emissions. And that is something that we would like to avoid. So from this viewpoint, we need to find and calibrate between two extremes. We want to make sure that we don't break the interconnection queue on one hand, and on the other hand, we want to have this lumpy demand distributed preferably in locations where they're going to cause and require less interventions from the grid side, whether it's transmission expansion or co-location with other generation resources.
Great. Cooper, anything you'd want to add on that?
Yeah, I think that one thing we didn't cover, that this more granular approach to measuring the emissions of workloads, what it unlocks is actually something like carbon-aware compute. So one thing that Google does is we have a carbon-aware compute engine where we move workloads around based on the emissions of the local grids. So you can basically move workloads when there's clean energy being supplied by a grid, either by location or the time of day, if kind of there's the sun is shining or if the wind is blowing on turbines. I think the other interesting thing in the context of AI specifically is kind of a question around latency. So in the past, data centers did need to be pretty geographically distributed in order to have low latency for customers. You need the actual location of the data to be close to where the customers are asking for it. AI actually has currently a little bit less of a need for low latency, just because people don't expect the queries to come back quite as quickly as they do for something like a Google search. And so you can kind of get away with having both the training being located somewhere where there's more clean energy, and sometimes in some cases, even when the inference or when you're kind of asking questions to the models, those can actually be more centrally located in places with clean energy rather than it being, sitting right next to the customer, because they have an expectation that the query would come back in 2 to 3 minutes instead of 300 milliseconds or something like that.
Yeah, and Cooper, that's something that you just mentioned relates to a question that I'll ask more broadly, but in terms of was it carbon compute? Was that the name of the
Carbon-aware compute, yeah.
So this is going to be a super goofy way to ask this question, but I'm going to ask it anyway. Is AI playing a role in actually allowing you guys to do the carbon compute as well? And that reflects some of the questions that are coming in, which is, is there could there at least be a virtuous cycle here where AI is making some of these decisions actually better and more efficient than would be made otherwise? So I don't know if that's a particular example of that, but I'm curious if it is, or if you have other examples where that's happening.
Yeah, many people think about AI only as these chatbots that are coming out, these large language models that have really taken off in the last few years. But there are many other applications of AI, and Google has many applications that are increasing the sustainability of different sectors. So we have things like contrails, where we monitor contrails that are being created in the atmosphere and try to reduce those, which actually reduces the warming effect of airplanes. And then things like Tapestry, where we're trying to model the grid as closely as possible, and then apply AI to do things like load balancing and things like that to modernize the grid in a kind of more technologically advanced way. And there's definitely opportunities for AI to drive sustainable growth. And we're thinking about that in addition to the fact that we want to reduce the impact of developing AI when it comes to the energy consumption that it has.
Yeah, and I've definitely heard of grid optimization as one of the primary ways where people are actually looking to deploy AI. Yuri, I don't know if you have any insights into that too, but I feel like even in the ether, that's something that I've heard as being, top of mind for people.
Yeah, I mean, as in any other sector, as in any other critical infrastructure, it has an enormous potential to improve operations of the power grid. It has nothing to do with the deployment of data centers. It's just using AI to make better decisions on how to dispatch generation assets or how to basically deploy certain corrective measures to make sure that we operate the power system more reliably or more affordably. It has tremendous potential because for many years we've been relying on what is known as deterministic optimization. We've been putting a lot of patches on top of it to accommodate the growth in renewables and deal with their uncertainty, to accommodate energy storage, and so on and so forth. So as a result of it, AI provides us an opportunity to revisit this holistic set of tools. Maybe one day we're going to have a very large language model telling dispatchers what exactly to do, but that's for now is a dream, but might not necessarily be a fiction.
I like it. Before we move away from the geography question, there's sort of a related set of questions, a couple of which have come through. I know we're focused on the electricity side here, but I wanted to invite either of you to comment. There are a couple of questions on water usage as well, and how that's either factored into where data centers are located, or where kind of as new power sources are being developed, where those are located, if they require cooling and other things that might have high water demand. So maybe I'll start with Yuri this time. Do you have any reflections on the water questions and how those are playing into siting decisions?
Absolutely. And I would try to generalize this answer. It's not only water, it's actually all of the resources that are needed to run data centers and the power grid that will supply electricity towards them. It's not only data centers per se, it's also scope 1 and scope 3 processes that are going to be affected and going to be accounted for when we're talking about data centers. So that is becoming increasingly valuable. Our focus on energy is primarily dedicated by the fact that it's the current constraint, but it does not mean that moving forward, water is not going to become constrained. That's why having a holistic LCA framework that would account for all potential resources needed for data centers, including chips, critical materials, water, and so on and so forth, is so critical because we also live in the age of climate change. So it is not exactly clear or not exactly straightforward to guarantee if water is available in a certain location right now, it will be available there like 10, 15 years from now. One of the biggest examples would be, for example, Colorado River or Mississippi River, which have some issues recently. So in that sense, we need to think how to co-design this consideration into what we are doing and what other forms of cooling exist out there. One thing, and it should be recognized for their leadership, ARPA-E, a US federal agency, is very much interested in synergies between data centers and energy technologies. An example of this synergy, which sounds like fiction, but it actually has been demo tested, is when you put the data centers in a lake or in an ocean, and that works as a natural cooling for it. So from this viewpoint, if we really want to think about resource conservation, we need to think about that holistically, and there could be better or different ways of undermining certain constraints. The issue with energy is that it is a very expensive, very time-consuming, and very complex issue to deal with that needs to be dealt with now.
Yeah. Cooper, anything you'd want to add? On the,
Yeah, my background is
yeah, go ahead.
much more on the carbon emissions side. I think the interesting thing to me about water and compared to carbon emissions is it's much more of a local issue, right? You have to think about the water scarcity of a specific region rather than the kind of the global impact of global emissions. And so that's something that kind of other colleagues of mine who are much more familiar with water are thinking a lot about. So in 2001, we announced a water stewardship goal where we aim to replenish 120% of the freshwater volume we consume on average across all of our offices and data centers by 2030. And in 2023, we became the first major cloud provider to report site level water usage numbers. And so we're really trying to make sure that we consume water responsibly because it obviously is an important piece of the data center ecosystem when it comes to cooling these data centers.
Yeah. And I just want to comment too that both of your responses really spoke to another question that we have, which I think you just answered, but just to give a shout out to this question that, life cycle assessments can often narrowly focus on emissions. And so this questioner was asking, how can policy frameworks evolve to think about those things like mining impacts, supply chain instability. So I think you did a really nice job of, again, just highlighting how this is a place where we really have to think holistically, for sure. So, okay, I'm gonna now turn to a series of I'll call them technology or fuel specific questions. And we've hinted at some of these, but there are a number that have come in, for example, around nuclear and geothermal. And I would say kind of the general gist of these questions is, what is the role for for nuclear energy, for geothermal, to be deployed in service of AI demand? Electric power demand. And there's also kind of a follow-up, Yuri, on your point about challenges with natural gas siting or natural gas plant development at this moment in time too. So I guess I'm going to invite you both to sort of talk about, again, the theme of this conversation is opportunities and challenges, right? It gets to be a little cliche, but where do you see opportunities around nuclear, around geothermal, and then where do you see challenges associated with any of the technologies that we've been discussing? Cooper, maybe I can start with you on this one.
Yeah, I think the thing that I would maybe start with is I think there's a long-term view that needs to be thought about here in terms of having advanced technologies that can support clean energy load growth into the future. And so we're definitely thinking about that quite a bit at Google, and we have a few innovative investments in that space. The first one that I would talk about is we recently signed the first corporate agreement with Kairos Power, which is nuclear energy from small modular reactors with the hopes of bringing new firm carbon-free energy to the grid to help meet some of these needs for AI energy demands. And I think importantly, we've kind of brought this to bear as in kind of order book type framework versus one reactor at a time in order to kind of send that demand signal to the space to show that there is desire and demand to kind of bring this type of generation onto the grid. The other is around geothermal, working with Fervo Energy, trying to bring more interesting kind of innovative opportunities for that type of advanced energy generation. And so, yeah, kind of as I alluded to the beginning, bringing new technologies on the grid is something that's very important to us because we recognize that in the near term, wind and solar are the necessary technologies to make sure that we can both reach the load that we need for operations and also meet our clean energy goals. But over time, it's going to get more and more difficult as other sectors electrify. And so we want to make sure that we are driving the ecosystem to change in a responsible way so that we can, one, kind of make sure that we can operate sustainably, but also get more of that demand, that generation online for other industries.
Yeah, great. And Yuri, one thing that I realized our questioners didn't really ask about, but you made a passing reference to, and I'd welcome your thoughts on, is this combination of renewables and battery storage as well. So I would just invite you, if you have any comments about how people are embracing that as a combination that might allow for a steadier source of power that these data centers need. But in general, take it away. Nuclear, geothermal, batteries plus renewables. Anything you want to comment on?
I think I agree with everything that Cooper and you just brought up. I mean, these are all sources, and I just want to emphasize that in order to support AI growth and the growth of other sectors, we should go with a diverse set of energy portfolio. We should not stick with one option. Our consideration should be triaging between three things: cost, technologies needs to be cost competitive. Two, this technologies needs to be reliable and provide either firm or synchronized supply when you have a combination of resources where each resource provides at different times. And we need to make sure that we serve our customers, as Cooper pointed out, with sustainable energy as they require. How do we do that? Well, different technologies will take priority across different points of time, but as we move forward and as our planning horizon and look ahead horizon increases, a lot of options like geothermal, small modular reactors, they become more and more accessible. Maybe in a distant future, we're going to have floating offshore wind, which is an interesting way of thinking about data centers, and so on and so forth. So there is no single technology that will solve this problem as a magic bullet. We just need to understand what kind of subset of technologies would work best in different parts of country and how we can possibly organize their operations in a way when they complement one another rather than create problems. And one example is, for example, in California or ERCOT, that there is congestion, whether transmission congestion or due to some other reasons, which cause renewables to curtail electricity right now. What that means is that if we think about deploying energy storage in these locations, if we think of coupling these locations with batteries, they can naturally provide a spin-off to support data center operations while taking advantage of resource which is being curtailed that is wasted right now. So there are plenty of opportunities. We just need to target them in terms of the need, in terms of the location, and in terms of timing.
Great. Really interesting stuff. Okay, Cooper, the next set of questions is for you, and they relate to AI use and prompts and training. And so there are kind of two, I'll lump two questions together here. So for example, Yuri mentioned that adding words like please and thank you can add to the compute needed and therefore the energy needed. So would you have any suggestions about ways to design prompts, for leaving the please and thank you aside, which has other benefits, but other ways to design prompts with this kind of energy usage question in mind? And then the second one about AI use and training is, so the questioner asks, I understand that AI training is very energy intensive, but is there information on the percentage of energy for inference overall versus training? Let me turn to you for those two.
Yeah, of course, happy to. So on the first question around please and thank you, I think it's an interesting question, and it largely boils down to the technical side on tokens in terms of the model tokens that are being used both on the input and the output side. And so basically what tokens are is you can kind of think of them almost as syllables. And when you ask the question to a model, the model thinks about that broken down almost as syllables of words. The longer your request is, the more tokens that are input into the model. And then also the longer the response is, the more output tokens there are from the model. And the energy usage of the model inference is proportional to the number of tokens. And so you can actually reduce the energy usage of the model base by reducing maybe the number of input tokens you're putting in, or the expectation for how long the output ends up being. But what I would maybe add to that as a subtlety, which I think is maybe even more interesting, is this also depends on the size of the model. So when you see different models that are coming out from model providers, you oftentimes see these really powerful models that are sometimes determined to be and they often have very large context windows for tokens, and they're designed to do things like read an entire book, like a Charles Dickens book, and then you can ask it a question about somewhere in the book, and then it gives you an answer. You don't really need that for all applications. And so maybe more than thinking about reducing your query to not have please and thank you in it, just maybe make sure that you're using the right sized model for the type of application that you have. So Google has a chatbot called Gemini. We have a pro version of the model that is very powerful, but we also have kind of a version of the model called Flash, which is much less powerful and probably best for smaller types of queries. And so more than prompt engineering, I would maybe suggest that folks just make sure they're kind of looking at the size of the model to make sure that they're not using a hammer when they could be using a screwdriver. On the other question around inference versus training, there's definitely this difference in terms of how those will grow over time. You can kind of almost imagine training as a capital expenditure where a lot of the energy usage is being done upfront, and you're training this massive AI model with a lot of data and a lot of compute. And then the inference is more like an OpEx expenditure where basically that will scale with a number of users that are end up using the model that you have developed. So that there's not much data out there on energy usage of inference versus training, but I think it's something that the industry is trying to get more clear about, because as there's more and more adoption of these models, you expect inference to grow more quickly than training grows, because a lot of the training energy usage kind of was front loaded, and then inference will increase over time. So keep your eyes out, I think, for more transparency on the difference between those two environmental impacts.
Great. Yuri, you have mentioned states a few times, and I wanted to turn now to our set of kind of state level questions and some policy driven questions, if that's okay with you. So I know you mentioned California, you mentioned ERCOT, which is the kind of organizing body in Texas. And so there's one question here that specifically asks, in the realm of policy, do we know which states are farthest ahead in regulating AI energy use and or tying it to renewables? So let me start by asking you that. I'm not sure if that's something that you necessarily look into, but I have a feeling you might know the answer. So
I think it is true to say that states around the country, they differ in their approach to AI. And even if you take two states such as Virginia and Maryland, which are located very close by, they have completely different attitudes and they pursue the same goal. They would like to harvest as many possible data centers, but they already started to observe some impacts of it, which related to the fact that in order to accommodate data centers, in order to have the supply, in order to have transmission, what unavoidably happens is that some of these impacts are going to be passed on their consumers. And that is the biggest concern for the majority of the states, that while they want to be part of this AI revolution, they want to minimize cost burden on regular users. And that is what is being used. Another issue which is related here is that it's very often that when you cross state boundaries, which happens often, for example, Maryland and Virginia are part of the same interconnection, but they're part of different states. They also have to account for a different environment. And it's impossible to support data centers in Virginia without making some grid upgrades in Maryland. And then the question is, who's going to pay for it? Because the costs are incurred in one part of the state and the other one is going to reap the benefits. So we need to find a cost allocation framework which help us to fairly allocate the costs and benefits of AI infrastructure in a way that is going to serve populations of all states. So that's one important issue across the state policy angle. The other thing is that when you navigate state policy, the attitudes toward data centers are going to be very diverse, just in the same way how we had different attitudes toward renewable technologies as a whole, or even specific renewable technologies and battery storage. Some states prefer to have legal mandates, for example, RPS. Some states went Wild West and didn't have any legal requirements, and they still did fairly well. One example being Texas, right? One of the national leaders in adoption of wind and solar. One of the most important things moving forward, I believe, will be something that states are grasping their attention with, how they can collocate energy used by data centers and hydrogen, because it's a miraculous silver bullet resource that everyone is talking about, but has not yet been implemented at scale. But different states look very differently at it, and that could be another opportunity for us to bring different states on the same page, because hydrogen provides flexibility and support that has not been observed with other resources.
Mm-hmm. That's great. And I think, I know you mentioned there are no silver bullets, and yet maybe hydrogen is the only, just kidding.
Yeah.
So there's a follow-up question here too that I think is relevant for both of you. So Yuri, I'll start with you again, but Cooper, I'm sure you'll have thoughts on this too. So, are there any policy discussions happening at the federal or state level about requiring tracking of AI energy use? And I can imagine that would feed into a number of these conversations about allocation of all sorts of costs and sort of understanding who might pay for some of these upgrades, but it's based on that foundation of data around how much energy is actually being used where. So are any, either at the federal level or at the state level, is there any kind of policy driver coming out around different or better tracking of AI usage data, energy usage data?
So from the carbon policy, the United States has been carbon myopic in some way. We don't have a national carbon policy, whether it's a tax or nationwide trade system. So from that viewpoint, I don't see that happening anytime soon for AI or for any other sector. However, some states, like the state of California with cap and trade mechanism, have developed a way to recognize carbon burden of certain sectors and their impact on society. And that provides a reasonable framework for the entire state. How this will generalize into other states, well, that's up to the states to decide. But I think there will be, if there will be further action which is going to target AI and carbon impacts of AI, it is unlikely to be at the federal level unless we're talking about like some major policy shift in DC, which I don't see coming soon. It may happen in later. And actually, it might be driven by external forces, because one of the things that Cooper mentioned in his comments about customers is that a lot of foreign customers that would like to see sustainable computing and they want to remain to be Google clients. And if their jurisdictions in Europe or somewhere else in the world will require some carbon guarantees or carbon act, that will be an important driver to make sure that American services are competitive around the world.
Mm-hmm.
And from my viewpoint, the ideal solution would be to have a carbon tax of some way or nationwide carbon trading system, but it is impossible under the current climate, and it has been impossible for decades. So it's not that a sudden shift in administration or in priorities would certainly create a pathway towards achieving this goal.
Mm-hmm. Mm-hmm. Yeah, boy, on the day that Canadians are going to vote for two candidates, both of whom were anti-carbon tax, I think there are a lot of lessons learned about the political economy of those economy-wide policies for sure. So, but I hear you, there are, at the federal level, we're in a moment where it's likely to be a couple of years before climate policy is picked up holistically. And so at the state level, I don't know, Cooper, do you have anything to add about kind of policy drivers for some of this accounting?
Yeah, maybe just to put a finer point on the specific things that we're seeing. I think it's exactly what Yuri was mentioning, mostly coming out of the EU when it comes to customers asking for more granularity and transparency on emissions data. It's the CSRD directive that's mostly driving customers to ask us for more granular emissions data. When it comes to AI specifically, the EU AI Act is starting to kind of centralize around expectations for disclosing energy of AI models as well. So tracking both of those closely.
Great. Okay, well, I think I have time. I'm going to try to squeeze in two more questions for you guys, and I know we're getting on towards time here. So if I can ask you to keep these brief, but I want to make sure to get to both of them. So I'll just ask them both, and I'll let you guys answer as you will. So one is about, I just lost it here. Oh, it was about collaboration between companies and grid operators. So obviously, the fates are intertwined between some of the AI companies and these grid operators. And so I guess if either of you can comment on sort of what the conversations and connections between those two key players here look like, I think our audience would love to know. And then I'm going to end on a super deep intellectual question because I love it. So one viewer asks, so how do the speakers suggest resolving, I'm going to say Jevons paradox, I think I've got that right, or the rebound effect, where improved efficiency paradoxically leads to increased resource use through expanded adoption? So given that, and I'm going to keep reading here, this very literate question here. So given that demand for compute seems virtually unlimited, are efficiency gains alone insufficient to meet data center demand for energy? So two very different questions, but equally interesting, I think. So Cooper, why don't I start with you? Feel free to comment on either or both, and then Yuri, I'll let you have the final word on the questions.
Yeah, I'll maybe start off with the first question and then hand it off to Yuri, and then we can go to the second, because it's the Jevons paradox question is a big one. When it comes to how we collaborate with grid operators, I think there's a lot of eagerness to work collaboratively with operators, because data centers have this interesting property where they are dynamic and we have control over what the load ends up looking like. And so you can imagine data centers working hand in hand with grid operators to kind of develop mechanisms like demand response and things like that. And I think that's something that, especially with AI workloads that sometimes do have flexibility in terms of the fungibility where you can move those workloads around during time of day, like training. It doesn't need to necessarily be trained, all at the same time. We can move that around and be flexible with grid operators. I think there's a lot of eagerness for collaboration there. And opportunities for us to think about how that might be deployed across other sectors as well, kind of being the tip of the spear here in terms of modernizing the grid. We can kind of think of data centers as an opportunity to drive forward some kind of more innovative thinking on how industry and grid operators can work hand in hand to develop a robust and reliable system.
Yeah, great. Yuri, anything you'd want to add?
I fully agree. One of the most resonating issues for me here is that collaboration across this boundary has always been contained within respective domain, and we've been following a siloed approach. Utilities and power grid operators, they like to think in terms of megawatts and gigawatts, and in Cooper's paper, the loads that HEAP draws is like on the scale of kilowatts, right? So that shows the big discrepancy on the scale of several orders of magnitude. So from the viewpoint of the grid, it is very important to look into data centers and see what is under the hood, and to bring this information close to real time for power system operators to really connect to it. So in Texas, for example, when they operate wind farms, there is an opt cable that basically connects turbines to the control room. We essentially need to think about the feedback that would go between data centers and the power grid. We also need to have a way to engage end users, whether corporate or residential, because that's the most important thing to understand how they use these resources and what kind of flexibility they have, so that we can send proper incentives, or instead of monetary incentives, it could be friendly nudges. So it is very important to narrow this gap between the kilowatts and megawatts and gigawatts that we use in the grid space.
Great.
And going to your second question.
Yes, please. All right, you guys have 30 seconds on this incredibly complex area, but let me turn it.
I'll just say one thing then. From my viewpoint, the Stone Age ended not because we ran out of stones, but because we learned how to do things better. The same is applicable to compute and to energy. Yes, the use of compute will increase, but so will improve technology, and so will we create new mechanisms how to allocate limited resources. We're going to rethink business model for compute. We're going to rethink business model for energy. It is just a way of creating business models that help us to allocate limited resources. And I really appreciate the question, but I think the solution is already we know. It is to be more efficient.
I like it.
And
I also like the positive note. Cooper.
I'll briefly add to that. I think when you think about what might actually limit that growth, I think it's probably the value that it can provide. And so if we're finding that it's not providing value, then it will start to be limited. But I think there is real value into thinking about the unit efficiencies to make sure that we're developing it as responsibly as possible.
Great. Well, thank you both so much. Thank you to all the great questions that came in, to so many people for chiming in. I really feel honored to have been a part of this conversation with all of you. And Yuri, Cooper, thank you so much. I'm going to turn it back to Laura to close us out.
Well, I first want to thank you, Kristen, for moderating that fantastic conversation. Yuri and Cooper, thank you for sharing all these fascinating developments in the AI and energy space. To our audience, thank you for joining us today. Thank you for your interest, your great questions, and sharing all your thoughts on Slido. We do read all the feedback you send us, so please do take our survey or email us at climatecrossroads@nas.edu with your thoughts or reflections from today's programming. This conversation was recorded and will be available to view on this same webpage immediately after we end. Our May conversation is going to look at the impacts of climate on coral reefs. The registration is live, so please head over there and sign up. And finally, thanks again to my colleagues, Kasia Kornecki, Jasmine Victoria Bryant, and Kim Bob at the Board on Energy and Environmental Systems. And as always, a big thanks to my team and all the National Academy staff who supported this event today behind the scenes. Take care, everyone, and we'll see you in May.